driving force. So what are the three driving forces for double replacement reaction?
Precipitation.
Precipitation. In order to determine if there's a precipitate or not, you need to know the solubility rules. And so precipitate is an insoluble solid. So insoluble solid forms, and we have precipitation. If there's no insoluble solid, the reaction still might occur if one of these other two driving forces are present. What are the other two driving forces that we look for? Yeah, both of those. So the second one is we look for gas formation or effervescence. And there are a number of things I didn't realize that. For example, if we have hydrogen ions and carbonate ions, we form carbonic acid, but carbonic acid is not stable. Carbonic acid spontaneously decomposes into water and carbon dioxide. And so whenever we form carbonic acid, we cross it out and replace it with water and carbon dioxide. And so an example of that would have been this one, magnesium carbonate plus hydrochloric acid. What does this form? It's going to form magnesium chloride, which would be MgCl2, magnesium is +2, and hydrogen carbonate. Hydrogen and carbonate form carbonic acid. And so carbonic acid, we never leave there. We decompose it into H2O liquid plus CO2 gas. So in this case, we don't form any precipitate. Here, chlorides, bromides, and iodides are all soluble except for yeah. And so this is not one of the exceptions, so this is A. So there's no precipitate here, but we still have a reaction because we formed a gas here. This would be the example of the CE. Magnesium carbonate. Carbonates are all insoluble except for carbonates, phosphates, and chromates are all insoluble except for group 1 and ammonium. So this is actually insoluble. Where that's going to impact us is in the IE. You know, in the IE, what do we do? This is an insoluble solid, so we leave it alone. HCl is a strong acid, so we dissociate that. 2H plus 2Cl minus. Magnesium chloride is a soluble salt, so we dissociate that into Mg2 plus 2 chloride. Water we don't do anything with, that stays as is, and same with CO2. Those are non-electrolytes. This would be the IE, and then finally the NIE, we would get rid of the spectator. So chloride looks like a spectator, but everything else reacts. So magnesium carbonate solid plus 2H plus is going to give us magnesium 2 plus H2O liquid plus CO2 gas. So these are the species that are reacting here, the products that are forming. But the driving force here, actually there are two driving forces here. So one's gas formation. What else forms gas before we talk about the other driving force? So carbonic acid. Another thing that looks like carbonic acid also forms gas, and that's this acid. What's this acid called?
Sulfuric acid?
Sulfuric or sulfurous? Sulfurous acid. Sulfurous acid is also unstable. This decomposes into H2O liquid plus SO. What do you think? SO3? SO2. SO2 is a toxic gas, and so this would be gas formation. And one other thing decomposes. CO2 and SO2 are what we call nonpolar. We're going to talk about polarity later, like non-polar versus polar. But these are unlike water, so they don't really dissolve. But this one is going to be like water, and that is when ammonium hydroxide decomposes in ammonia and water. We'll talk about what makes something like water or unlike. Ammonia dissolves significantly in water. CO2 and SO2 don't. And so ammonia and a little bit might come off as a gas. So this really doesn't effervesce much with ammonia, but these two will effervesce a lot. We could also form other gases like HCN. If we take hydrogen and cyanide, those combine to make hydrocyanic acid or hydrogen cyanide gas. H2S, gas, etc. And so hydrogen ions and cyanide and hydrogen and sulfide will just make gas straight away, whereas these ones will make a compound that decomposes into a gas. And so we look for gas formation. And the last thing we look for is stronger acid to weaker acid. In this case, this is what we have here. We have a stronger acid, HCl, going to weaker acid, carbonic acid. And so we actually have two driving forces for this. Although the carbonic acid decomposes immediately, this water and CO2. CO2 is also acidic. Although it doesn't look like an acid because there's no H. It's a different kind of acid. So basically we only need one driving force here, which would be gas formation or effervescence. That's for double replacement. None of these work for single replacement. What's the driving force for single replacement? There's only one driving force for single replacement. What is that? You have a single replacement reaction, none of these work.
The driving force is the activity, right?
The activity, right. Exactly. So for single replacement, we only look for the activity going from more active to less active. That would be the driving force. That would be the downhill direction. And so single replacement, the problem is that sometimes people get confused. You can't use these driving forces for single replacement reactions. And so all these are double replacement style reactions, and so we need those three driving forces for all of these. We have single replacement reactions later. Are these double replacement or single replacement? Double replacement. How can I tell? It's because it has the AB plus CD pattern. Same thing with these. These are all double replacement. They subcategorize it, but we don't have to subcategorize these. Treat them all the same. So maybe we'll just get some practice here. Predicting the products of double replacement. So I'm not going to write them down, but I'll just name them. What's the name of this? Yeah, lead, nitrate, except the problem is there are two lead ions that are common. Yeah, that would be lead 2 nitrate plus potassium iodide. And what does it form? Well, it's going to form lead 2 iodide. Lead 2 iodide. What's the formula for lead 2 iodide? Can you do it in your head?
PBI2.
PBI2 is correct. Is PBI2 soluble or insoluble? And so we have to go back to chlorides, bromides, and the iodides are all soluble except for silver, lead, and mercury. And so we're going to get a precipitate here. And the precipitate is going to be lead 2 iodide. What's the other product? The other product would be potassium with nitrate. That would be called potassium nitrate, KNO3 is the other product. All potassium salts are soluble. Yeah. Any group 1 cation, lithium, sodium, potassium, rubidium, cesium, they're all going to be soluble. So, but we don't need 2 precipitates. We only need 1 precipitate. So if we get a precipitate PBI2, we balance this, and we can get the CE, the IE, and the NIE. How about this? What's this called?
I have a question.
Uh-huh.
What do you mean by we only need 1 precipitate?
Oh, so in this case, the other product doesn't precipitate. So if we have lead-2 nitrate plus potassium iodide, this is going to give us lead-2 iodide and potassium nitrate. The lead-2 iodide precipitates, forms an insoluble solid, but this one does not precipitate. And so we balance this. I usually leave off the aqueous just to save a little time. And then if it's non-aqueous, that is solid, liquid, gas, I write the state in there. And so here's the driving force. Driving force is precipitation of lead-2 iodide. So, since I broke this up here, we might as well finish this. This would be called the CE. What would the IE look like? Do we ionize the strong electrolytes? The strong electrolytes are the strong acids, strong bases, and soluble salts. So here, this is a soluble salt. All nitrates are soluble. It doesn't matter what it's attached to. All nitrates are soluble, and so we ionize it into the ions. So this is going to form Pb2 plus and 2 nitrates. All potassium salts are soluble. And so this is going to form 2 potassium ions and 2 iodine ions. PbI2 is insoluble, so we just leave that alone. But potassium nitrate is a soluble salt, so that's going to leave 2 potassium ions and 2 nitrate ions. And then looking at the spectators here, nitrate, potassium are spectators. So the net ion equation will be Pb2 plus 2 iodides yields PbI2 solid. So we expect the reaction to go back. On the test, I'm not going to subcategorize these. You'll have a double replacement. You'll have to figure out, is it precipitation, is it gas formation, or is it stronger acid, weaker acid, or none of those? How about this one, 31, or actually 30? What's this called?
Cobalt-3 nitrate.
Cobalt-3 nitrate?
Isn't that take the bigger one? I think it's
One way you can figure out the charge is what's the subscript here on cobalt? 1. We use all 1. So nitrate's 1 minus, but cobalt is 2 plus. And so this would be cobalt-2 nitrate, no?
Yeah.
Not cobalt-2. So cobalt-2 nitrate, and what's this called?
Potassium phosphate.
Potassium phosphate. And when this reacts, it's going to form cobalt-2 phosphate. Cobalt-2 phosphate, the quick way to get the formula for that is, we know cobalt is 2 plus. We know phosphate is what charge? 3 minus. And so what a lot of people do, and this works, is we just drop these as a subscript. So cobalt is going to be CO3PO42. And so it's like cross multiplying. Phosphates, carbonates, and chromates are all soluble or all insoluble, except for group 1 and ammonium. And so this is not an exception. So this is insoluble. We're going to get a precipitate of cobalt to phosphate. And so there's a driving force here. What's the other product? The other product is going to be potassium nitrate, KO3, potassium nitrate. And then we balance it. Figure it out from there. Here we have potassium chlorine. All potassium salts are soluble. Moreover, all chlorate salts are soluble. Chlorates, nitrates, and acetates are all soluble. And so this is why this is aqueous. And then we have a magnesium, what's this? Magnesium nitrate, nitrite. Did you have the rules for nitrites?
Yeah.
Now we have a nitrate, but we don't have to worry about it because they're telling us it's aqueous. So normally what we do is, if we don't have the rule, we'll just assume it behaves similarly to the 8. So nitrite would be similar to nitrate in terms of solubility. Sulfites would be similar to sulfates in terms of solubility. We'll just assume that, or we look it up. Where can we look up solubilities? There are different places to look up solubilities. One place is this, the CRC Handbook of Chemistry and Physics. This is on the 103rd edition. They revise this every year, so it's been around for over 100 years. Here they'll have the solubility data. The CRC Handbook of Chemistry and Physics, they have this at the library. Wikipedia is similar. The format of the entries in Wikipedia is similar to the data that you find in the CRC Handbook. That's one. The other big one is the Merck Index. I don't know what edition they are on the Merck Index, but you can rent it for $25 or buy a used one. Merck Index, like the drug company, Merck. Merck Index has more drugs and biologicals in there than the CRC. So our library has both the CRC Handbook of Chemistry and Physics, the Merck Index, as well as the Encyclopedia of Chemistry. The Encyclopedia of Chemistry will have a bunch of stuff there as well. Or we could just look it up online, magnesium nitrite. See what it says. I like Wikipedia, the way they have it organized. They might not have it. Yeah, it's not in Wikipedia. There are other sources. ChemPub or PubChem is the National Library of Medicine. They have it, but the way the information is organized, it's not so easy to find the solubility. When we look at the computed properties here, component properties, related compounds, literature, it's not easy to find. It's not so well organized, I think. All Right, so we say it's soluble. What does it form? It's going to form potassium nitrate. Potassium nitrate is soluble, potassium salt. And magnesium chlorate. All chlorates, acetates, and nitrates are all soluble. So in number 31, this is what we do here. Both of those are soluble, so that means there's no precipitate. Do either of those decompose into a gas? Are we going from a stronger acid to weaker acid? No. And so this is what we say. NR for double replacement. So we don't expect any double replacement reactions to occur here. So that would be 31 here. Well, how about 32? Barium nitrate's aqueous. We'd expect that all nitrate salts are soluble. This one, I don't know. We'd have to look at sulfates. Sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium. So this is not one of the exceptions, so it's soluble. So most sulfates are soluble. This is going to produce barium sulfate. Barium sulfate does not precipitate. So sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium. So barium sulfate is one of the exceptions. And so what we're going to do is we're going to precipitate out barium sulfate. What's the formula for barium sulfate? Barium is 2+, sulfate is what charge? So you can go here and reverse this. So if we bring the 2 over here, that means sulfate's 2-. And
I think you just need to resize it a bit. Next to the X and resize it.
I think this is not the one. Oh, yeah. So we're going to get a precipitated barium sulfate. So sulfate is a 2-, barium is a 2+, so it's just BaSO4. What is this called again?
Iron.
Iron 2 or iron 3?
Iron 3.
Iron 3. So you can bring this 3s here, so it'd be iron 3 sulfate. And barium. So the other product of this would be iron nitrate. Well, which iron is it? Iron 2 or iron 3? Iron 3 nitrate, which would be FeNO3. And so we get a precipitate there. So this one is okay. How about 33? What's this called? Silver nitrate and lithium bromide. And this is not all nitrate salts are soluble. Lithium salts are soluble, so those are both aqueous. That's fine. And we're going to produce silver bromide. Chlorides, bromides, and or except for silver, lead 2, and mercury 1. So silver bromide is going to precipitate. And the other product is going to be lithium nitrate which all group 1 salts are soluble and all nitrate salts are soluble, so that's soluble. So this one's going to precipitate off silver bromide, BGBr. Let's take a look at number 34. What's this called? Is it nickel 2 or nickel 3? Nickel 2 bromide plus. Okay, chlorides, bromides, and iodides are all soluble except for silver, lead, and mercury, lead 2 and mercury 1. And so this is soluble as you'd expect. All potassium salts are soluble, so this is soluble as well. This is going to form nickel 2 hydroxide. So hydroxides are all insoluble except for which ones? Group 1, ammonium, and calcium, strontium, barium. So this isn't none of those. So nickel 2 hydroxide should be insoluble and it should precipitate. So we're going to get a precipitated nickel 2 hydroxide. The other product is going to be potassium bromide. Yeah, which is soluble. A nickel 2 hydroxide, what's the formula for that? Yeah. Ni2OH2 or NiOH2? NiOH2.
Yes, nickel 2.
All right, what's the next? I don't know why this keeps doing this. So can you name those? Yeah. Sodium sulfate or sodium sulfide. Problem is sulfites, we didn't have the rules for sulfites, right? And so, yeah, we're going to assume it's similar to sulfate. In fact, that's what they say down here. Where do they say? I don't know why they didn't say this earlier. For number 76, they say sulfites follow the same solubility guidelines as sulfates. So we know what sulfates are. This would have been more helpful on the previous page here. And so what do we have here? Chloride. So this is not one of the exceptions. Silver, lead, and mercury was the exception, so this is soluble like we'd expect. And sulfates, well, this we don't even have to worry because this is group 1. All group 1 salts are soluble. And so that's it. What is it going to make? It's going to make zinc and all right, so zinc sulfite, will that precipitate? You think? Zinc sulfite precipitate? No. Sodium chloride precipitate? No. And so we get no precipitate. Then we look for what? So zinc sulfite decompose into a gas? Sodium chloride doesn't. Then we look for a stronger acid too. There are no acids here. And so we would say no reaction. Well, no reaction for 35. 36. We have some sodium. So all sodium salts are soluble, all nitrate salts are soluble. So this is soluble. Sodium nitrate and barium hydroxide. Hydroxides are insoluble, but this happens to be a soluble one. Hydroxides are insoluble except for which one? Group 1 It's not group 1. Ammonium and calcium, strontium, barium. So this is one of the exceptions on the hydroxide. So this is soluble. So what does this form? This is going to form sodium hydroxide and barium nitrate. So sodium hydroxide is sodium salt, that doesn't precipitate. Barium nitrate is a nitrate salt, that doesn't precipitate. So we get no precipitate here. Does sodium hydroxide decompose into gas? No. Does barium nitrate? No. No gas formation. And then we have no acid.
Professor,
Uh-huh.
why isn't it precipitate?
I'm sorry?
Why isn't it precipitate?
Why doesn't it precipitate? Let's take a look. Because neither are soluble, insoluble. We need an insoluble solid to form. So when I take sodium nitrate plus barium hydroxide, this is going to form sodium hydroxide, which is aqueous, and barium nitrate, which is aqueous.
Oh, okay.
So both of those are aqueous. All sodium salts are aqueous and all nitrate salts are aqueous. And so this form we just write NR for double replacement. I'm going to draw the force for that. How about these here? What do you call that? Sodium nitrite and well, it's aqueous. So if it's aqueous, we'll call it an acid name because the H begins with an H. Hydroiodic acid. So sodium nitrite with hydroiodic acid. What's this going to form? It's going to form sodium iodide and hydrogen. Hydrogen nitrite we call not nitric, because hydrogen nitrate we call nitric acid. Hydrogen nitrite we call nitrous acid. So HI you have memorized as one of the 7. Yeah. How about nitrous acid? No, it's weaker. So we're going from a stronger acid, HI, to weaker acid, HNO2.
Nitrous acid is liquid at room temperature?
Nitrous acid is, because there's water present, we're just going to say aqueous. And so we just say HNO2 aqueous.
I mean glacial.
Glacial, like acetic acid? Acetic acid is liquid at room temperature. Nitrous acid is likely a liquid. I don't know actually what the state is. So we would look it up in what pure nitrous acid is. But this PubMed isn't so easy to find the data. So we probably look in Wikipedia. Wikipedia has it a little easier as far as the organization goes. If Wikipedia even has it. Let's see, does Wikipedia have it?
Look up like the state of matter of pure HNO2 rather than
The state of matter for what?
like pure and HNO2 instead of just searching up pure HNO2.
Oh yeah, that's true. Let me take a look. So what's nice is they have it organized like this here. Pale blue solution, only known in solution or as a gas. So it's a gas actually, in pure form. Otherwise, at room temperature. I suppose at room, if you cool down the temperature, you can get it to liquefy, but it's a gas.
So it's a cryogenic oxidizer?
Cryogenic oxidizer?
Yeah.
Well, it's an oxidizer here, but cryogenic, I mean, it could be an oxidizer at room temperature too. It doesn't have to be cold for it to be an oxidizer.
I was trying to select my rocket fuel.
Oh, for rocket fuel? Yeah. Well, if it's a gas, it's not going to make that great of a rocket fuel. And then if
Gas reaction is actually very efficient.
it's very efficient, but the problem with the gas is that you can't pack as much gas into a tank. You know, this is one of the problems is the range. If it's a gas, there's a lot of empty space, and so you aren't going to have as much fuel. Therefore, you aren't going to have as much range. And so you'll probably want to liquefy it and then let it evaporate to a gas. That's better. We have a lot of things that you can, like butane. You know, butane's a liquid, but it evaporates pretty fast into a gas.
I'm gonna go with nitrous acid and kerosene.
Nitrous acid and kerosene? That would work, probably. Liquid nitrous acid and liquid kerosene? Yeah, that would work. Okay. So let's go back to this. How about this? Potassium nitrite, potassium sulfur soluble, and hydrochloric acid. And so this is going to form potassium chloride and hydrogen nitride. Hydrogen nitride is nitrous acid, so this is similar. This will form nitrous acid as well. So we're going from a stronger acid HCl to a weaker acid, nitrous acid. And this one you don't have to name. Here. This one's called potassium propanoate, and then this is mixed with, what's this acid called? Perchloric acid. Perchloric acid is correct. And this is going to form potassium and hydrogen propanoate. Hydrogen propanoate is called propanoic acid. And so this one is a bit more tricky because of that acid. You're not familiar with that acid, but you don't have to be familiar with that acid because you know the 7 common strong acids. Is perchloric acid one of the 7 common strong acids? No. And so this one doesn't precipitate. You know, all potassium salts are soluble, and acids are soluble. So we'd call it HC3H5O3. These 5 hydrogens are not acidic, it's just this one. This is a monoprotic acid. And so we have no precipitate, but we do have stronger acid, which perchloric is one of the strongest acids, to weaker acid. This has got to be a weaker acid because it's not one of the strong acids that we memorized. And so this one is a little bit more complicated because this acid's not on the chart. We should be able to figure it out. Okay, next. This is and hydroiodic acid. And this is going to form sodium iodide and what's HOH? Water. So we have sodium iodide and water. This is the classic, what we call acid-base neutralization, which forms salt and water. A driving force for this, sodium salts are soluble in water. And therefore, the driving force would be stronger acid to weaker acid. The weaker acid in this case is going to be water. So stronger acid to weaker acid here. That would be the driving force. Okay, what's the next one here? This is rubidium plus hydrofluoric acid. And so what does that produce? Rubidium fluoride, which is group 1 salt, and water. There's a major difference between these two. And this will be the CE for this. The IE is, okay, sodium hydroxide. This is sodium salt. Sodium salts are soluble, so that ionizes into sodium ions and hydroxide ions. Hydroiodic acid, is that a strong acid?
Yes.
Yes. It's one of the 7 strong acids. So this is going to form H plus and I minus. Sodium iodide is a soluble salt, so that forms sodium ions plus iodide. And then water is not a strong acid, strong base or strong electron, soluble salt, so it stays alone. And then the NIE for this is just going to be, let's see, sodium spectator, iodide is a spectator. And I'll just flip this around. So we have H plus OH minus yields H2O liquid. And so what we have here is we have strong acid plus strong base yields water. And so this is what we call acid-base neutralization. In number 43, we have a strong base, like sodium hydroxide. The strong base is rubidium hydroxide. It's a strong base. Except, is hydrofluoric acid one of the 7 common strong acids? No, so the major difference here is HI is a strong acid, HF is actually a weak acid. But this is going to produce rubidium fluoride and water. Well, which one do you think is stronger? Both of these are weak acids, HF and water, but which one do you think is stronger? HF. And so we call this the stronger acid. This is going to the weaker acid here. But HF itself is not a strong acid. S just stands for stronger acid. And so when we look at the IE for this, rubidium hydroxide, that's a soluble salt. So it's going to form rubidium ions and hydroxide ions. But HF is not a strong acid. We only ionize strong acids, strong bases, and soluble salts. So HF stays together. Rubidium fluoride is a soluble salt, so that's going to ionize into rubidium ions and fluoride ions. And then water just stays by itself. And so there's a big difference in the NIE for this. The NIE looks totally different. The NIE is going to be, rubidium will cancel, but it's going to be hydroxide plus HF yields fluoride plus H2O. Yes. So all we need is that one driving force. And the difference is we do not ionize weak acids. This is a weak acid. What's this number 44 called? Acetic acid plus barium hydroxide. Barium hydroxide is a strong base. We'll have a reaction there. We're going to form hydrogen with hydroxide, which is water, and barium acetate. And there's no precipitate. Acetates are soluble. We do go from stronger acid, acetic acid, to weaker acid, water. Okay. 44. Let's take a look at 45. We have here. What's this called? Magnesium carbonate, right? Is that right? Magnesium carbonates, phosphates, and chromates are all insoluble except for group 1 and ammonium. So is this one of the exceptions? No, this is not one of the exceptions. This is just wrong. This should be magnesium carbonate S for solid. That's a typo. Even though this book is in what edition? 11th edition? 7th edition? 7th edition, there's still errors in the 7th edition of the book. So magnesium carbonate solid plus, okay, that's okay. What is this going to produce? This is going to produce magnesium and hydrogen carbonate. So I already did this one. I did this one on the board earlier.
I have a question. How do you know if solution breaks down into gas?
It's one of the ones you memorize. So if it forms hydrogen carbonate or carbonic acid, then it breaks down into a gas. If it forms hydrogen sulfite or sulfurous acid, it breaks down into a gas. And if it forms ammonium hydroxide, it breaks down into a gas.
We just need to know those three.
Yeah. And so look at this next one. We have hydrogen sulfite. Well, hydrogen sulfite is sulfurous acid. Sulfurous acid breaks down into a gas. And so in this one, we're going to have gas formation and calcium chloride, calcium chloride. And so it's, if we're looking at this next reaction here, we would write it like this. HCl plus CaSO3. Did they get this state right? And so sulfites are like sulfates. So if sulfates are like sulfates, then what are the rules for sulfates? Sulfates are all soluble except for
Silver, lead, and mercury.
Silver, lead.
yeah, silver, lead, mercury, calcium, strontium, barium. So calcium is one of the exceptions. So it's solid. So this is correct. So if it's aqueous, I don't write it. If it's solid, I'll write it. And this is going to form hydrogen sulfide. Hydrogen sulfide's formula will be what? Well, hydrogen's plus 1, sulfide's minus 2. So I'll need 2 hydrogens for every sulfide. We'll get H2SO3. And calcium is a plus 2, and chloride's a minus 1. So I'll need 2 chlorides for every calcium. All right, this is an acid, so it's soluble. The chlorides, bromides, and iodides are all soluble except for silver, lead, mercury. So this is not an exception. This is soluble. So we get no precipitate here. But we do have gas formation because sulfurous acid is unstable. And so what I do is I'll just cross it out and instead write H2O liquid plus SO2 gas. And so the driving force is this, the formation of SO2 gas. To balance it, I'll need 2 HCl's, and then it should be balanced.
Yeah.
This is the CE. The IE, do I ionize HCl? Yes, strong acid. 2H plus, 2Cl minus. Do I ionize calcium sulfite?
No.
No, it's insoluble, so we just leave that alone. Water, leave alone. Sulfur dioxide, leave alone. How about calcium chloride? Calcium chloride is a soluble salt. Soluble salts are strong electrolytes, we ionize those. And so as far as spectators go, I have 2 chlorides, and then it looks like this. And so the NIE is going to be 2H plus calcium sulfite, solid, yields H2O liquid plus SO2 gas plus calcium ion. This next one, sodium sulfite, which is aqueous sodium salt, and what's this acid called? Chloric acid. This is going to form sodium chlorate and hydrogen sulfide. Hydrogen sulfide is sulfuric acid, and as we saw before, it decomposes here. So this is going to be a gas former. How about this one here, 48? what's this called? Ammonium sulfate, and all ammonium salts are soluble, all sodium salts are soluble. This is going to form ammonium and sodium. Well, sodium sulfate is not going to precipitate, and ammonium hydroxide won't precipitate, but you should know something about ammonium hydroxide. That is, ammonium hydroxide is, it spontaneously decomposes into ammonia and water. And so that's what we expect here. And so you have to memorize those gas forming, the ones that decompose there, unfortunately. So, the strong bases kind of the opposite of the strong acids in a way. We're only going to look at one class of strong bases, and that's the soluble hydroxide. Some of these strong bases you can buy at the supermarket, like this one. Sodium hydroxide, you can buy pure sodium hydroxide or close to it. Pure sodium hydroxide. It's a white solid. Buy this solid. You know what they call it in the supermarket? This household chemical. Not Epsom salt. Lye. When I looked, it was Red Devil lye. But they have this one. They didn't have any of this. This Red Crown High Test lye, they didn't have that. They didn't have this one. This is Red Hot Devil lye. I just know Red Devil lye is a common one. That's the one that was at Ralph's. But they're all the same, pretty much. 99+% purity. Meats, food, chemical codex. Do you want to eat this stuff? No. You know what they use it? You know what section of the supermarket this is in? In the drain cleaner section. Yeah, lye is used to clean drains. So this is why this one, household lye drain cleaner. Danger, poison, causes severe burns. Yes, causes severe burns. Don't use this for food. Even if it's food grade. I don't know, food grade. What would be? And so you can buy that sodium hydroxide. They also sell magnesium hydroxide in the supermarket. Do you know what they call magnesium hydroxide? Milk of magnesia. Have you ever heard of that? Milk of magnesia. Maybe you've never taken it before. What's it for? It's for like upset stomach. I've had it. Except it would look pink. The milk of magnesia that I had, they put pink food color in there. This is white. It's very viscous. You see how viscous it is? It's like a paste. In fact, it tastes pasty when you have it. You know, there's a paste, and it doesn't taste very good.
Like edible pink.
Yeah, it's like eating paint or something like that. It's just not pleasant. But the thing is, this, both of these are hydroxides. And so are both of these strong bases? Sodium hydroxide is what we call a strong base. Is magnesium hydroxide a strong base? No, it's not. Why not? It has two hydroxides for every magnesium. This only has one hydroxide for every sodium. Seems like twice as much hydroxide.
Is it the same thing with like an acid that they don't disassociate at the same power?
Yeah, right. It's exactly like that. Hydroxides are all soluble except for, or no, that's wrong. Hydroxides aren't all soluble. Hydroxides are all insoluble except for group 1, ammonium, and calcium, strontium, and barium.
So do bases, when they react, do they want to go from a stronger base to a weaker base?
Yes.
Or a weaker base to stronger?
No, stronger base to weaker base would be downhill, yeah. So this is why this is like this paste. It's a paste because it's not very soluble. And so what you have is you have white magnesium hydroxide, which is like a precipitate, and you got this pasty white suspension, this precipitate that is a whole bunch of solid crystals of magnesium hydroxide floating around in there. That's why it tastes so bad. Whereas, this is soluble. So if you mix this with water, it should dissolve, right? No problem. Lye itself, when you go and buy that in the supermarket, it's salty. So you don't have to do that, but it dissolves in water. So this is the lye here. So I'm thinking about it. Wouldn't you much rather drink like a clear liquid of sodium hydroxide than a pasty suspension of magnesium hydroxide?
No.
Wouldn't that be better?
No.
No? All right. Like, for example, okay, how about this? If you ran out of drain cleaner, would magnesium hydroxide make an effective drain cleaner? You would pour that paste in, it really wouldn't make it very effective. And the same thing here. If you ran out of milk and magnesia, could you substitute some sodium hydroxide, lye, for that? No. And so, in terms of reactivity, which one's much more aggressive? The sodium hydroxide. So we call this a strong base. The strong bases are the soluble hydroxides. And the insoluble hydroxides, we don't consider strong bases. We consider those weak bases. They're weak bases because they don't produce as much hydroxide. Just like strong acids produce lots of hydronium, bases produce hydroxide. And so most bases are weak because most hydroxides are insoluble. I mean, most of the hydroxide bases are weak, like magnesium hydroxide, iron, 2-hydroxide iron, 3-hydroxide, et cetera, et cetera. And so this is weak. This is kind of interesting. Change the topic here, but there's lead poisoning. If you have lead poisoning, there are 2 drugs that are available for this. Do you know what the 2 drugs are that are available? One of them is calcium EDTA. The other one is sodium EDTA here. And so EDTA is a funny anion. It's huge. Ethylene diamine tetraacetate anion, or acetate ion. And so we have the calcium salt of that and the sodium salt of that. And what happens is the EDTA is the active ingredient. Sodium is like a spectator. It doesn't do anything. So if you have a lead ion, the EDTA grabs onto the lead and holds onto it tightly that the lead can't react with any other proteins in your body. So lead can cause damage. And so what the EDTA does is it chelates. Chelate is just grabs it like a claw and holds onto it so it can't react with other stuff. And so this is called chelation therapy. Chelating agents and chelation therapy. Chelation therapy. And so chelating agents bind lead in soft tissues and are used in the treatment of lead poisoning, basically. And so we have two chelating agents available, calcium EDTA and sodium EDTA. Which one do you think is more aggressive? Sodium EDTA is much more aggressive. Wouldn't you expect that? It's like, which one's more aggressive, sodium hydroxide or magnesium hydroxide? Sodium hydroxide is more aggressive. Right. So sodium EDTA is not administered to children. It's a bit too aggressive for children. And sodium EDTA is only if you have huge amounts of lead and the lead is causing damage and you need to do something quickly. And so for acute lead toxicity. So in February 2005, a girl aged 2 years who was tested for blood lead during routine health surveillance had a capillary BLL, blood lead level of 47 micrograms per deciliter. A venous BLL of 48 micrograms per deciliter obtained 12 days later confirmed that she had a lot of blood, of lead. A complete blood count and iron study conducted concurrently revealed low serum iron levels and borderline anemia. On February 28, 2005, the girl was admitted to a local medical center for combined oral and intravenous chelation therapy. And so they're going to try to chelate all that lead in her blood to neutralize it. The patient's blood electrolytes at admission were within normal limits. Initial medication orders included intravenous sodium EDTA and oral Saxamer, an agent primarily used for treatment of lead poisoning. The medication order was subsequently corrected by the pediatric resident to intravenous calcium EDTA. So at 4 p.m. on the day of admission, the patient received her first dose of intravenous calcium EDTA. 300 milligrams and 100 milliliters of normal saline at 25 milliliters per hour. At 4:35 p.m., she was administered 200 milligrams of oral Saxamer. Her vital signs remained normal throughout the night. At 4 a.m. the next day, a dose of intravenous sodium EDTA instead of intravenous calcium EDTA was administered. An hour later, the patient's serum calcium had decreased to 5.2 milligrams per deciliter. Normal value would be 8.5 to 10.5 for pediatric. At 7:05 a.m., the child's mother noticed that the child was limp and not breathing. Bedside procedures did not restore normal cardiac rhythm, and the cardiac resuscitation code was called at 7:25 a.m. The child had no palpable pulse or audible heartbeat. The repeat laboratory values for serum drawn at 7:55 a.m. indicated that the serum calcium level was less than 5 milligrams per deciliter despite repeated doses of calcium chloride. All attempts at resuscitation failed and the girl was pronounced dead at 8:12 a.m. So it's like between 5 p.m. and 8 a.m. the next day, all this happened.
Was this because of the lead that she died or the mucin?
She didn't die because of the lead. She died because of the sodium EDTA. Can you imagine that? Can you imagine, you're the one who gave the girl drain cleaner instead of milk and magnesia. Can you imagine being the responsible person for that? That would be too heavy. I mean, this is tragic. This is really tragic. I mean, she shouldn't have died in the first place. I mean, if you think in terms of like drain cleaner versus milk and magnesia, you wouldn't think you'd give it. But anyway, if it happened once, if it happened once, it's too much. But 5-year-old boy dead, 53-year-old woman dead, etc. This isn't all the cases. There are a lot of cases. So do people still use it? Well, Well, the CDC came up with a recommendation.
And at this point, it just looks like they're giving them more poison.
Right. And so the CDC recommendation is to get rid of sodium EDTA in the hospital. So the question, do they still use it? I don't know, but the CDC recommends that they get rid of it. They get rid of it so that nobody can make this mistake. It would be like, we should get rid of the sodium hydroxide out of your house. That would be safer. That way nobody would eat that.
So the reason that we know that sodium is more reactive than like sodium EDTA would be more reactive than calcium EDTA is because of the reactivity table,
Not because of the reactivity table. It's because of how much. Like a base is hydroxide, an acid is H+. The more H+ you have, the stronger the acid. The more H+ you have, the more acidic the solution. And so, for example, hydrochloric acid produces a certain amount of H+, and acetic acid also produces H+, but a much smaller amount. And so acetic acid we call a weak acid, hydrochloric acid we call a strong acid. And so it depends on how much H+. Well, the same can be said about bases. Bases, the more strong, the more basic the solution, the more powerful the base, the more hydroxide we have. And so the difference between these two is this one, we have lots of hydroxide. So if you were to drink this instead of this, you're going to all of a sudden have lots of hydroxide that can react with other things in your body. So this is what's going to cause the trouble. Whereas if you were to drink this, there's very little hydroxide. Most of the hydroxide is locked up in the lattice. And so this stuff is going to dissolve, but as it dissolves, it slowly releases the hydroxide. So we don't get hit with a huge amount of hydroxide right away. And so this one produces a lot less hydroxide. Well, the same thing with over here. And this is what happened with this. If you have sodium EDTA, that means the sodium and the EDTA aren't strongly bound. So this would be like soluble. This is going to break up into ions, sodium ions and EDTA. And so the EDTA will be free to react with the lead, preferably. With calcium EDTA, the calcium sticks to the EDTA, making it less reactive. There's less free EDTA to react. Therefore, this is the reason why this is so much more aggressive, is because there's going to be a lot more EDTA that can react freely than this, or the calcium. Now, EDTA doesn't discriminate between ions. And so what happens with what happened to her, the girl, is this. The EDTA is looking for ions. And it's going to look for ions it's more attracted to. Sodium ions, it's not so much. And so these dissociate. But EDTA likes calcium ions, 2+ and 3+ ions, preferably. And so what happened to the girl was that the girl was administered sodium EDTA, and the EDTA started attacking all the calcium. And her calcium level dropped. Their calcium level dropped so low that it caused heart failure. Because, heart requires certain ion balance or electrolyte balance in there. And so that was the problem. But they tried to fix that by injecting her with doses of calcium chloride. Because the EDTA were, obviously you want the EDTA to attack the lead, but it attacks anything it can. And so here, they tried to fix the problem. So the EDTA was looking for cations it prefers over sodium. And so what they did was they did repeated doses of calcium chloride to compensate for all the calcium that the EDTA was taking. And so her calcium level was here, 5.2. Normally it's 8.5, and then it decreased further. So her calcium went below 5 here. Should have been 8.5 to 10.5 for normal function. And so calcium level 1 too low, heart failure.
So could we assume that calcium EDTA is not soluble, but sodium is?
Kind of that way. Calcium EDTA is still soluble because this is not the whole formula. The whole formula, they shorten the formula. Calcium EDTA is not technically all calcium. It's this. EDTA is a 4- anion. And normally we don't see very many 4-, but this one is not any problem, because it's not 4- on a monatomic. There's 4- on the oxygens. I don't want the tetraacetate. So this is an acid. It's a tetraprotic acid. You remove these hydrogens and then you form the anion. And so there's a negative charge here, 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 here. And so that gives it the 4- charge. And so if it were like this, then you'd expect it to be insoluble. But it's this. It has 2 sodiums and 1 calcium. Sodium EDTA, they call this sodium EDTA, but that's not really correct. The correct formula for sodium EDTA is Na4 EDTA. And these 4 sodiums can come off. So this is kind of halfway to precipitation. So even if they administered her this, well, it's a lot less aggressive than this. This is going to take the calciums. You don't want things to precipitate. So even calcium EDTA, the shape of this prevents it from precipitating out very easily. And so even this it's encapsulated into a little ball, and those balls don't really crystallize very easily. But in that sense, this is a lot less reactive than this. So in a sense, you can think of it in terms of precipitation and that kind of thing, but it's not exactly, but effectively similar. So I was thinking, if the person who injected that knew something about solubility rules, they might have been able to catch that error. What do you think? Maybe? Or, if there are 2 drugs on the shelf, you had sodium and calcium, maybe could have thought, the sodium and magnesium. Or maybe, maybe it's all the same. To a lot of people, this is the same thing. They're both hydroxides. Hydroxides are bases. So they're interchangeable, but they aren't exactly. Well, anyway, to avoid that and to avoid thinking how that happened, because it happened twice, right? The first one is it was originally prescribed sodium. That was wrong. It's clearly marked on the bottle that it's not for use for children, I'm sure. Okay, so for reactions, does this make sense though? A little bit. So we have our test next week. And the reactions that we're going to cover for this test, one is going to be the element plus element yields compound. So in these types of reactions, one element loses, the element further left in the periodic table. One element gains, the element further right in the periodic table gains. Two is the reverse of this one. That is, a compound decomposes into the element. So it's just a reverse of this. There could be more than one element. Same thing with one. Three, we have double replacement. So the double replacement, you're going to have the standard ones. Standard ones being the ones in the homework here. 4, you'll have single replacements. Single replacements will be like the standard ones here in the homework as well. These. 5, you're going to have combustion of hydrocarbons, CXHY or CXHYOZ, carbon, hydrogen, and oxygen containing compounds.
Is that also in the homework, or would we have to
Yeah.
make the notes?
This is in the homework and the notes. 6, you remember all the exceptions for single replacement reactions where single replacement didn't work? That's the chart method. The chart method, though, I've been thinking about this one here. Chart method and aqueous ammonia, we're not going to have it on this test. Did anybody get these, the chart method?
I understood it in class.
Okay. We'll give you more time for the chart method. And aqueous ammonia we'll talk about in the lab, but that's not going to be on the test. So just your basic reactions here, somewhat similar to the homework problems there. The chart method is not really in these two chapters, chapter 8 and 9, and aqueous ammonia is not in there as well. So not on this exam here. So single replacement, what's the driving force for single replacement? Activity series. So you're going to be given the activity series or a chart that you can figure it out. But these are pretty straightforward, right? Copper plus, what's this? Is going to yield copper 2 sulfate or copper 1 sulfate? Copper 2 sulfate and lithium metal. And so in this case, you don't need the activity series. What's more reactive, copper metal or lithium metal? Lithium is much more reactive. So this is going from less active copper to more active lithium. And so there's no driving force here. You know about lithium is a very dangerous metal, and they're lithium fired. So 19, no reaction. It doesn't matter if it precipitate forms or gas forms. when we look at activity series. Okay, how about 20? What's this? SN. 10. SN is 10.
Should we have that one?
Yeah, 10 is pretty common. You can memorize that. 10 and what's this called? Zinc nitrate is going to form 10 2 nitrate or 10 4 nitrate? Yeah, 10 2 nitrate is much more common. So it goes to 10 2 nitrate and zinc metal. Then we have to figure out which one's more reactive, tin or zinc. In this particular case, I would use a chart here. Lithium is the most reactive metal. And then I go here, zinc is here and tin's here. So zinc is more reactive than tin. Tin's more stable. And so in this particular reaction, we're going from tin to zinc metal. So we're going from tin to zinc metal is going to be less stable. This is actually upside down. And so this one we expect no reaction, no single replacement reaction here, etc. So you see problems similar to this. One difference though is usually I write the name and you write the formula. So rather than giving you the formula Li2SO4, I'll give you the name, lithium sulfate. And rather than giving you the formula Cu, I'll just tell you copper. So I write this as copper is combined with lithium sulfate solution. Tin is combined with zinc nitrate solution. Barium and hydrochloric acid react. Magnesium and copper 2 sulfate solution react. Zinc and nitric acid react. Other ones like this would be a typical combustion. Propane I'm not going to expect you to know the formula. So that's C3H8 is combusted or burned. And so you have to figure out, when we have combustion, what do we add to it? And what do we form?
Water and carbon dioxide.
Yeah, and so all these will do the same thing. Right, so is that clear what's going to be on the test for reactions?
Yeah,
So
so
I think-
and then all the metric conversions and stuff are on it as well.
Yeah. And other things.
Remember at the beginning of the class, like in chapter 2, there were some conversion factors that we have to remember other than like the simple ones.
Mm-hmm.
We're not going to be given a conversion sheet, correct?
Correct, but some of the conversions you don't have to have memorized. The conversions you have to have memorized are the definitions, like 1,000 milliliters in a liter, that one. Or there's one definition that's weird, and that is centimeters to inches. How many centimeters are in an inch?
2.5.
2.54 centimeters in
So
an inch.
would that be the only one?
Yeah, that's the only weird one. The other ones you don't have to memorize, like liters to gallons. How many liters in a gallon? You might have it memorized, 3.785, but that's only good to 4 sig figs. And so that's going to be a given. If you forget it, that's fine. I'll give it to you. 3.785 liters in a gallon. Also, you don't have to have memorized the number of grams in a pound. How many grams are in a pound?
453.
453.6. So if you have a flashcard and you're memorizing it, you don't have to memorize that one.
I'm glad.
Okay. Yeah, it's 453.6 grams.
So the centimeter to inch one should be the only
Centimeters to inch one, and then the metric ones you should know.
one.
The other one is for gas pressures. You should know that 1 atmosphere is equal to 14.7 psi or 760 millimeters of mercury or 760 torr. Pascals, you don't have to memorize that. So one or bar, one atmosphere is equal to 1.01325 bar. You don't have to
What
memorize
was the
that.
mercury conversion from 1 atmosphere?
1 atmosphere is 760 millimeters of mercury.
60.
You should know that. If you forget a conversion factor, you're going to ask me. You can ask me during the test, and if it's one that you should know, then there'll be a deduction. But it's better than,
Not being able to answer all.
not being able to calculate something. All right, we'll take a break here and then start up again. Okay, what I was thinking for the test for chapter 10 is we're just going to have, I'm going to finish chapter 10 before the exam, but for the exam I'm just going to have 10.1 and 10.2 on there. So 10.3 through 10.9 will be tested later. Okay, so just 10.1 and 10.2. Chapter 10 deals with quantity relationships and chemical reactions. So for the homework, you don't have to turn in all of chapter 10 homework. For homework, just turn in sections 10.1 through 10.2, or you can just turn it all in. So the quantity relationships are like this, the balanced chemical equation. There are two ways to visualize this. One is by particles, so 4 ammonium molecules, 5 oxygen molecules. So this is combustion of ammonia. In combustion of ammonia, we're going to form nitrogen oxide, or oxides of nitrogen. So either nitric oxide or nitrogen monoxide or other oxides of nitrogen and water. So this is in terms of molecules, but we can also visualize this in terms of moles. So 4 moles of ammonia molecules, 5 moles of oxygen, etc. And so here, in terms of molecules, 308 molecules of ammonia, we could use the ratio that we get from the equation. That is, for every 4 moles of ammonia, or molecules of ammonia, we have 5 molecules of O2 react. So we can do simple quantity relationships like this. How many molecules of oxygen do we need? Well, for 4 molecules of ammonia, we need 5. For 308, we just use some dimensional analysis. We calculate 385 molecules of O2. We don't really work with individual molecules or individual particles. We normally work with much larger quantities. That is moles of molecules. So we have these are called the conversion factors. So I'm not going to do too much with these here. But at the center of the stoichiometry map, this is stoichiometry map, is a mole to mole conversion. It doesn't have to be reactants to products, it can be anything. So it's going to be moles of A to moles of B. We're going to use the mole ratio from the balanced chemical equation. And so we don't really work with particulates that much. And so this is the main thing we're going to be dealing with. And so typical calculation is pretty straightforward. Let's say I have 3.20 moles of ammonia. How many moles of water would I produce? I just look at the ratio. It's a 6-to-4 ratio there. Okay. All right, and so the first thing we need is the balanced chemical equation. So let's do this. Let's write the equation for the combustion of ethane. Ethane has a formula C2H6, and it's a gas. So go ahead and write the combustion equation for that. All right, so what did you get for heptane?
Plus 11O2
Plus 11O2.
is 7 CO2 and 8 H2O.
7 CO2 and
8 H2O.
8 H2O. CO2 is gas, H is liquid, O2 is gas. Look. Yep. That's what we have here. That's good. And so this is a little bit weird because, you know, we look at the stoichiometry map. We usually start with grams of A here going to moles of A, and then moles of A to moles of B to grams of B. But in this particular problem, we're going to be starting with moles of A here. And so we'll just go from moles of A to moles of B to grams of B. And so it's going to be 3.50 moles of heptane, C7H16. And then we'll do a mole to mole conversion. They want how many grams of oxygen, so B is going to be oxygen. And the mole ratios is going to be 11 moles of oxygen for every 1 mole of heptane. And so moles of heptane cancel. That leaves us with moles of oxygen. But we don't want to stop there. We're going to go to grams of oxygen. How do I go from moles of oxygen to grams of oxygen?
Divide by moles over.
Actually, we need the molar mass of oxygen. So the molar mass, each oxygen is 16, so we have 2 times 16.00, which is going to give us 32.00. That would be the molar mass. 32.00 grams of oxygen for every mole of oxygen from the periodic table. And so moles of oxygen cancel. This is going to give us grams of oxygen here. And so 3.5 times 32. 112 grams of 112.0. We're allowed 3 sig figs, so this is just going to go to 112 grams of oxygen O2.
Did you multiply by the 11?
Oh no, I didn't multiply by 11. Sorry, times 11. 1,232. Is that what you got? Now, we're allowed 3 sig figs, so usually people will convert this to scientific notation. 1.23 times 10 to the third grams of oxygen. We'll round it to 3 sig figs. All right, this is an unusual problem because we're starting with moles. Normally we start off with grams, something like that, or pounds, or something that's easy to measure. Moles aren't easy to measure, but they're easy to calculate if we have the grams, because we can just get the molar mass. Okay, are we okay with this one? All right, so the next one we're going to look at is the combustion of methane. Do you know what the formula of methane is? CH4. And so,
Memorize that one?
no, you don't have to have it memorized. So let's say if I have exactly 1 pound of methane, approximately how many pounds of CO2 will I burn? So if I combust exactly 1 pound of methane, how many pounds of CO2 will I burn? Let's do that calculation then. But first you'll have to figure out the balanced combustion reaction for methane. The same thing with liters to gallons. That one will be given. Bar, pascals, those will be given. Let me know when somebody has the answer. I saw the one person had 2.74
That's
pounds.
what I got.
That's what you got? Let's get that. 2.74 roughly. All right. Well, let's take a look at this calculation here. So if we start off with pounds of methane, then we'll want to go to grams because a gram to mole conversion is pretty common. So pounds of methane, 453.6 grams per pound. And that gives us 453.6 grams. But how many sig figs here? Since I said exactly, it's going to be infinite. And so far I have 4 sig figs. This conversion will only get 4 sig figs. And so now I have grams of methane. And so I need to relate grams and moles, and that's in molar mass. And so carbon is 12.01. Hydrogen is 101, and I have 4 of them. And so 4 hydrogens is going to give me 404. Gives me 16.05 grams per mole. And so that means 1 mole of methane weighs 16.05 grams. And so the grams of methane cancel, and that leaves us with moles of methane. And so all I have to do is mole to A, mole to B conversion. And so I'm interested in CO2. It's a 1-to-1 mole ratio. And so it's 1 mole of CO2 for every 1 mole of methane. And so I went from moles of A to moles of B, moles of B being CO2. And then I'm going to go from moles of CO2 to grams. Carbon is a 1201, oxygen 1600. So 2 oxygens is going to give me 32.00, which is going to be 44.01. So I have 44.01 grams of CO2 per mole of CO2. And so now I have grams of B, and I just need pounds of B. So 1 pound is equivalent to 453.6 grams. So the 453.6 cancels over here, and the grams of CO2 cancel, leaving me with pounds of CO2. So let's calculate this out here. So just take 4401 divided by 1605. Calculate 2.7420 pounds of CO2. So if I were to burn exactly 1 pound of methane, I would get, well, how many sig figs am I allowed? 4 sig figs. So rounding this to 4 sig figs, I would get 2.742 pounds of CO2. So I actually, that's 1 pound, it's almost triples, weight, but that's because CO2 weighs more. So 1 pound of methane yields that much CO2. How many pounds of water did we produce? Well, actually, maybe we'll do O2. How many pounds of O2 will I need to combust it? This is the next calculation. Pounds of O2 required for combustion. And so try this. This would be another stoichiometry problem here. So if I have 1 pound of methane, is that 2 pounds of oxygen? No, because they weigh different amounts. And so I would have to calculate how many pounds of oxygen I need to combust 1 pound of methane. 453.6 grams per pound. So we go pounds of methane, we go to moles of methane, or grams of methane to moles of methane. And so the only difference here is rather than going to moles of CO2, we're going to go to moles of O2. So the mole ratio here is 2 moles of O2 for every 1 mole of CH4, 2-to-1 ratio. And then from moles of O2 to grams of O2, each oxygen weighs 16, so this is going to be 32.00 grams of O2 per mole of O2. And then we'll convert it back to pounds. 1 pound is 453.6 grams.
It's gonna be 3.988.
3.988, okay. 3.988. Is that what other people got? Okay. 3.988 pounds. All right, so this equation here is our mole ratio. The mole ratio is going to be much better than a mass ratio. If we were to write mass ratios for everything like this, we have 1.000, let's say, pounds of methane. And so the mass ratio would be 1.000 CH4 plus, we just calculated how much oxygen, it's 3.988. 3.988 O2 yields, how much CO2 did we get? 2.7420 CO2 plus, how much water am I going to get? Now for water, there are 2 ways to determine how much water I'm going to get. One way is by mass balance. So the total mass on the left must equal the total mass on the right. And so what I could do is I could just add this up. It's going to be 4.988 pounds on the left. And so I should end up with 4.988 pounds. So then I can calculate it. 4.988 minus this is going to give me that. Or I can use stoichiometry. That is, just put it here, starting off with 1 pound of methane, and then just calculate how many pounds of H2O I'd form. And so either way I can do it. It seems like the quickest will just be to do mass balance here. That is 4.988 minus 2.742, 2.246. So we're going to be left with 2.246 pounds of water. All right, the mass ratio can be in any units. So it could be 1 pound of methane, or it could be 1 kilogram of methane. 1 kilogram of methane requires 3.988 kilograms of O2 to produce this many kilograms and this many kilograms. Or it could be grams. You know, this 1 gram requires about 4 grams of O2, produces about 3 grams of CO2 and about 2 grams of H2O. And so we could use any. But do you want to remember the mass ratios here? I mean, this is a lot easier to derive, right, than this. So even though we're really interested in mass to mass, we're going to have to go through the heart, that is a mole-to-mole conversion, because the equations are much easier to write in terms of moles or molecules than they are to write in terms of mass. And so the mass ratio is something we never write. You know, the mole ratio we always write, and therefore stoichiometry always follows that kind of pattern that we see over here. What if we burn another fuel? Let's see. What if we burned heptane? You know, if I burned a pound of heptane, would I form the same amount of CO2, more CO2, or less CO2? What would you guess? If I burned 1 pound of heptane instead of 1 pound of methane, would I get more CO2 or less CO2?
More.
More CO2? Okay, why don't you calculate that? How many pounds of CO2 do we get by burning 1 pound of heptane? C7H16. So if you recall, the balanced chemical equation is going to be a 1 to 11 to 7 to 8. 1 mole of heptane, 11 moles of O2 produces 7 moles of CO2 and 8 moles of water. So did anybody else get a different answer for this? Were there any questions about setting this one up? Okay. Yeah, if the units all worked out, then the setup would be good. All right. For the exam is going to be in 2 parts. The first part of the exam will be nomenclature. For nomenclature, there's going to be no calculator. It's just, you'll go through and you'll either write the formula or you'll name them. This might be, this is pretty long. It might be shorter because your test, you're going to have some reactions. This test, I didn't have reactions because I wanted to test it all at once. And then I made them do a lot of chart method. And so here, sometimes I'll throw in some bonus, in there as well. Most likely you'll have some bonus, but it might not be this, it might be something else. All right, any questions on the nomenclature?
Access to a periodic table.
Yeah, you'll have a periodic table. The periodic table will be similar to the one from the book. You'll have access for part 1 periodic table. For part 2, you'll have the periodic table plus this chart here. It'll look just like this. This is what I handed out earlier. You'll have the redox chart, like this, but the redox chart here has an upside down activity series. So lithium is the most active, and then it goes. And so you can see what the activity is. Here it's most, and then it becomes less and less active as you go up. You'll have some acids here as well. Part 2, I'd like you to bring a scantron. Like this. I think it's the 882 scantron, 882E. Is A, B, C, D, E. But if you have the numbered ones, it's fine. 1, 2, 3, 4, 5. But there are 50 questions on the side. And that's all. The scantron you can get at the library. There's, I think, a vending machine with scantrons in it. But I think the cost is higher than that. Do you know what the cost is in the library? Maybe 50 cents. I'm not sure. Or you can get it from the bookstore. The bookstore sells packs or individual. You can get a 6-pack of scantrons or buy them individually. And that's for the multiple choice here. And so in part 2, we'll start off with some multiple choice. A bunch of questions. In this case, there are 50 multiple choice. You might have more or less, depends. The general format of the test will look the same. And then you'll have some free response questions here. The free response for the chemical reactions will tack on here. So if I'm adding chemical reactions, let me shorten the nomenclature and shorten the multiple choice here, because this one didn't have any reactions. You're going to have, the element plus element combination, the single replacement, double replacement, and combustion. But they'll be the straightforward ones, not the exception ones. All right, so this is kind of the typical multiple choice questions you'll encounter. Did we already go through any of these? All right, like one, the scientific method must begin with a hypothesis. Is that true or false? Well, two things. Must, does it always have to begin with? No. Scientific method, lots of different ways you can approach that. And then typically it's hard to come up with hypotheses. It's not so easy. So a hypothesis usually comes, after. That's when we typically have a hypothesis. So I would say false. Two, chemists study the properties, composition, and blank of matter. Structure. D. Three, compounds have fixed properties. True. What has variable properties? Mixtures. Yeah. Because mixtures can have variable composition, which leads to variable properties. Four, isotopes are atoms of an element with different number of electrons. Ions are, but isotopes are different number of, not protons, neutrons. Five, chemists are concerned with blank forces.
Electrical.
Unlike charges attract.
True.
There's exactly 3.785 liters in a gallon.
Not exactly.
Not exactly, yeah. So this is only get to 4 sig figs. There are a lot more digits. This was rounded to 4 sig figs. You don't have to know this because I'll tell you the number, but you do have to know how precise that number is. And so this is false. 1 cubic inch is equivalent to how many cubic centimeters? Yeah, you'd have to cube. So 2.54 cubed is 16.387. And so it's A. Which measurement is more accurate?
The trailing,
Well, A is more precise, but is it more accurate? Normally higher precision means more accuracy, but you could have very high precision instruments. Let's say you go to the gas pump, and that's pretty precise, It's very precise, especially now, because a tiny bit, and then the dollars keep, It's pretty crazy. But it doesn't mean it's accurate. Those things have to be calibrated. They have to be calibrated continuously to maintain accuracy, even though they're very precise. The same thing with supermarket scales. They're very precise, but they aren't necessarily accurate. 10, how many significant figures are allowed in the answer to this?
2.
Okay, 1 because 0.07 has 1. Except this is subtraction.
Oh.
And the rules for subtraction are decimal places. So we're allowed how many? 1, 2. We're allowed 2 decimal places. And so when we do the subtraction, we're still going to have 2 decimal places. So it's going to be like 15.36. 15.36 is 2 decimal places and 4 sig figs. So here, it's not the number of sig figs, it's the number of decimal places. And then once we do that, then we'll figure out how many sig figs we have, and we're 4. That doesn't mean we're always at 4. We could do a subtraction and come out fewer than 4 sig figs. 11, how many sig figs in the number 0.07? That's 1. Yeah. 12, how many sig figs are there in 32 degrees? So this is the temperature conversion here, degrees C is equal to 9/5 degrees Fahrenheit plus 32 degrees.
It's by definition.
Yeah, it's by definition, so it'd be infinite. Yeah, this is infinite D. 13, the chemical properties of Na and Na plus differ.
Yes.
Yeah, that's true. These are totally different chemically. 14, oxidizers take electrons.
True.
True. Oxidizers take electrons, reducers lose electrons. 15, nitrogen can lose a max of 4 or gain a max of 3 electrons.
True.
That's true, based on the position in the periodic table. 16, atomic theory originated from observations. Atomic theory, yeah. That is, that matter consists of atoms.
Yes, it's true. True. With the left equation.
Yeah, did that come from observations or did that come from some hypothesis or some theory? No, it came from
Observation.
observations, yeah. Do you recall what the observation was?
The high deflection.
The gold foil experiment with the high deflection angles and that type of stuff proved the nuclear atom model. But
Oh, it was the conservation of mass.
yeah, the nuclear atom came after the atomic theory. Dalton didn't do atomic theory. Dalton didn't do the gold foil experiment. And so that was the conservation of mass. 17. How many sig figs are allowed in that calculation? 3. 18. A carbon atom weighing exactly 12 AMU can be found in nature.
Well, it's 14.
Well, this is carbon 14.
No, that's 14. That's true.
This is true because most carbon atoms are defined to weigh. What was the definition of the AMU?
There was an average one carbon is 12 exactly.
Yeah, one atom of carbon 12 is exactly 12.
I got it mixed up with carbon.
Yeah, there's carbon 14 and carbon 13. The average mass of carbon 12, carbon 13, and carbon 14 in nature is 12.01. Yeah. The 19 isotopes are numbered based on the number of, or the isotopes are numbered based on the atomic number or mass number? Yeah, the mass number. So oxygen 16, oxygen 17, oxygen 18. All the isotopes will have the same atomic number, but different mass numbers. 20, fluorine has only one naturally occurring isotope containing, fluorine has only one isotope. Can you tell me how many neutrons it has?
Yeah. 10 neutrons.
Yeah, how did you figure that out?
Subtract the mass number from the atomic number.
Yeah, okay.
Subtract the atomic from the mass.
Yeah, we can look at the average. The average is, the atomic mass there is 19 roughly. So that's correct. 10 is correct. Here's a conversion. 0.125 liters is equivalent to how many milliliters? 125. 22. 8,923 grams is equivalent to how many kilograms? 8.923. C. 23. 0.0561 grams is equivalent to how many milligrams?
Yeah, 56.1.
56.1 is correct. A. 24. Carbon monoxide, and carbon dioxide are all potential products of combustion.
True.
That's true. But even though they're all potential products of combustion, when we do a combustion reaction where we're writing out the equation, we ignore these two and we say only CO2 is produced. Otherwise, it's going to get or become a headache. 25, pool water having 1 ppm chlorine means 1 gram of chlorine per million grams of pool water.
Yes.
That's true. 26, water contains 11.2% hydrogen by mass. Calculate the number of grams of hydrogen in 250 grams of water. $28, correct. 27, the density of gold is approximately
It's super heavy. I forget.
Is that too much to
It's
have?
volume.
gold is one of the heavier elements on the periodic table, the most dense,
I think it's C.
10 times more dense than water.
No, it was 20.
It's 20
Yeah.
times, yeah. It's
Is
D.
that just something you memorize?
You memorize that what densities range from. They range from less than 1. Actually, for gases, do you know gases approximate density of a gas? 0.001 or 1 gram per liter. 1,000 times. So gases are about 1,000 times, and then the most dense elements are about 20 times. Like the most dense is like osmium, iridium. Those are the two most dense. And those are just a little over 20 grams per milliliter. And so you have to know the range, somewhat. Gold is slightly under 20. Gases and liquids are compressible.
Well,
Gases are
that's
compressible,
not compressible.
but liquids aren't. So this would be false. As the temperature increases, so does its kinetic energy.
True.
That's true. Air is a compound.
It's a mixture.
It's a mixture, yeah. It's not a compound. Distillation is a chemical separation technique that can be used to separate hydrogen from oxygen in water.
No, that's electrolysis.
Yeah, electrolysis. Distillation can't. Distillation is just used to purify water. Distillation is not chemical either. Distillation is physical. 32. Homogeneous matter is always pure.
I'll say true. Homogeneous,
Well, tap water. Is tap water pure
no.
water? No. And is tap water homogeneous?
Yeah.
Yeah. So I'd have to say false. 33. Sodium chloride is a molecular compound.
No, it's an ionic.
It's an ionic compound. It's metal and non-metal is ionic, so it's wrong. 34. A barometer is shown below. Is this what a barometer looks like?
Sometimes. Yeah. No. That's the gas weight measurement thing.
Yeah. We don't call it a barometer though, so this is false. This is called a manometer. If atmospheric pressure is 758 millimeters of mercury, then what is the gas pressure?
Divide that by
I think it's just
100 milliliters.
Well, what's pushing down on the left side?
atmosphere pressure.
758. What's pushing down on the right side?
The inside, the gas.
The gas inside here. And so what we do is we just set these equal here. So we have atmosphere plus the liquid, which is 255. So 758 plus 255 will equal this on the right side. Yeah. So 758 plus 255 will be 1013. So C is correct. .36. A tire shows 36.1 psig on the day with atmospheric pressure 14.6 psi. What is the absolute air pressure in the tire? So this is like Celsius is the relative temperature. The absolute temperature would be Kelvin. So what do I do to Celsius to convert it into Kelvin? Add 273. So this PSI is gauge pressure, which is relative. What do I do to gauge pressure to get absolute?
You always add 14.6.
I'd have to add 14.6. Here. Well, you would always add P atmospheric or barometric pressure. And so that's going to be 50.7 D. That's going to be the absolute pressure. The absolute pressure and the absolute temperature are always going to read higher than the relative because the relative has some arbitrary zero.
Wait. So if I put my tire at 50 psi, I'm over pressure. What is it?
If you pump your tire to 50 psi, then actually you have more than 50 psi in there.
So over pressure my tire?
No, because the rating on the tire is in gauge pressure. And so they didn't tell you what the rating is in absolute. And the reason is you didn't overpressure your tire because if you let out all the air, your tire's gone flat. But is there a perfect vacuum inside a flat tire?
No.
No, a flat tire just has air in there, but it's the same pressure as atmospheric pressure. And so when your tire is flat, that is empty, it's not really empty. There's gas there. If it were really empty, you'd have to suck out all the air that remained in there, which you'll never do. And so that's right. If you wanted to do this, you would just open the valve, let your pressure go to 0 psig, and then you get a vacuum pump, put the vacuum pump on the tire and start pumping out the remaining air in there. So it would be sucking it out, and then it would just crumble. And when you suck it all out, you'll remove another 14.6 psi. And so you'll be at negative 14.6 psig, which is 0 psi A. Does that make sense?
Yeah.
All right. So it's something like that. 37. 22.7 liters of a gas is cooled at constant pressure from 87 degrees C to 25 degrees C. What will the volume be at 25 degrees C? Well, is the volume going to be smaller or bigger?
It's gonna be small.
It's going to be smaller. So,
You can have temperature over volume
yeah.
and have that as a proportion, so you just find out.
Right. And so we set up a fraction. So it would be 25 over 87. No, we can't set it up. It has to be absolute temperature. So it'd be 298 over this one. And so it would be one of these ones here. So this is a combined gas law equation. I'm just about out of time. Do you want me to calculate it, or can you guys calculate this one? What is? 18.8 liters. And that was 298 divided by what? It should be on the top. It'd be 298 divided by. 18.8 is correct. And it would be 290 divided by this times 22.7. Well, anyway, we're out of time, so we'll stop here.
We'll go over the rest of it tomorrow.
We'll do the rest of it. We'll do some of it tomorrow and then some of it on Wednesday.
Let me know when you guys are kind of do that.